As I mentioned in a previous video, one of the things that you're going to see happen when it comes to vectors in the real world is that directions are typically given in terms of one of our cardinal or secondary directions. You won't typically hear of a vector being given in terms of its components, rather you'll hear it given in terms of a magnitude and a direction. Now on a typical map, this is the kind of thing that we would see. Never eat soggy waffles. These are referred to as our cardinal directions. Exactly halfway in between our cardinal directions will be our secondary directions. Halfway in between any of these will be northeast, southeast, southwest, northwest. So that'll be the angles that are exactly halfway in between true north, true east, etc. Now with that in mind, you'll notice that these 8 directions will take our unit circle or Cartesian plane or whatever you want to call it and slice it up into 8 equal slices. So if we take the entirety of 360 degrees and divide it 8 ways, the angles in between any of these 2 consecutive directions will be a 45-degree angle. Now that's going to come into play because we're going to see some polar representations of vectors in the following problem known as the airplane problem. It's quite wordy. Please feel free to pause the video to copy all of this down. An airplane normally travels at 550 miles per hour in still air. That's air that's just chilling, no wind blowing on it or anything like that. This airplane is pointed due north. As it flies, a wind blows in from the northeast. Now, if it blows in from the northeast, then the direction that it's actually traveling will be southwest, the opposite direction. So it blows in from the northeast at 60 miles per hour, blowing the plane slightly off course. Determine the resulting speed and bearing, or heading, or direction of the plane. Now, we're dealing with velocities in this problem, which is why we're going to be combining these velocities. We'll define 2 vectors. One of them is going to be the plane vector, which will denote p. So this will be the plane's velocity. And to the plane's velocity, I am going to be adding in the velocity of the wind. Now again, it blows in from the northeast, which means it'll be pointed in the direction of southwest. In comparison to 550 miles per hour, 60 miles per hour is not particularly big. So W, that'll be the wind's velocity. Our goal is going to be to find the sum of these 2 vectors. Now, geometrically, what that would look like is connecting the initial point of P to the terminal point of W. However, in order to add these 2 vectors together, we are going to need to represent them in terms of components. Currently, we don't have components. We have the polar representation of both of these. So with that in mind, as far as the plane is concerned, the magnitude of the plane's vector is going to be 550 miles per hour, and the direction is north. We need to come up with a representation of due north. And for that, I'm going to go back 2 sheets of paper and say that if we were to do the typical thing that we would do with the unit circle, we would define east to be 0 degrees, northeast 45 degrees, north 90 degrees, northwest 135 degrees, west would be 180 degrees, southwest would be 225, due south would be 270 degrees, and southeast would be 315 degrees. So with that in mind, the direction associated with true north is going to be a 90-degree angle. So to represent P in terms of its components, this should be the magnitude of P times the cosine of theta, and the magnitude of P times the sine of theta. This will convert from our polar form back into a component form, or Cartesian form. So it'll be 550 times the cosine of 90 degrees, and 550 times the sine of 90 degrees. Hopefully it's not shocking to find out that when something is traveling due north, its horizontal component is going to be 0, and it's all going to be directed in the vertical component. Now with that in mind, we're going to repeat the process for the wind vector. As far as the wind vector is concerned, the magnitude of the wind vector is 60 miles an hour, and the direction is going to be southwest. Once again, if it's traveling in from the northeast, then it's traveling in the direction of southwest. The angle that we had associated with southwest was 225 degrees, which is why we're going to use theta equals 225 degrees. That means that our wind vector is going to be magnitude of the wind vector times the cosine. I should probably use a different Greek letter for this, but it's too late. I'm committed. So magnitude was 60. Then we have the cosine of 225. Magnitude of 60 times the sine of 225. Now from the unit circle, both the cosine as well as the sine, cosine of 225 degrees is the same as the sine of 225 degrees, and both of those are equal to the negative square root of 2 over 2. Now the fact that they're both negative indicates that it's going to be moving to the left as well as down, which is what we would expect for a 225 degree angle. Multiplying by 60 and reducing the fraction is going to give us negative 30 square roots of 2 and negative 30 square roots of 2. One of my lights just burned out. I really hope that you guys can still see this okay. That looks pretty good. Alright. So with that in mind, now that we have both of these vectors in terms of their components, let's see if we can actually add them up. So p plus w is going to be equal to the vector 0, 550, plus the vector negative 30 square roots of 2, comma, negative 30 square roots of 2. Now with that in mind, adding these component-wise, we're going to get negative 30 square roots of 2, comma, 550 minus 30 square roots of 2. This vector describes the actual bearing, the actual direction, the actual heading of our plane. The problem is, we've got it interpreted in terms of its components. Now we need to convert back to polar. So to convert back to polar, first thing we're going to do is find the magnitude of this. And for that magnitude, we'll be taking the square root of the sum of the squares of the two components. Now, somewhere in here, it's probably going to be safe for us to go ahead and switch this over into a decimal approximation. So I'm going to grab my calculator and find out what this is equal to. So square root of, parentheses, negative 30 square roots of 2, close those parentheses and square the result, plus new set of parentheses, 550 minus 30 square roots of 2, close those parentheses and square the result. So input to the calculator should look just like what you have on your paper. This will be approximately equal to, we'll call that 509.34 miles per hour. The reason that I know it's miles per hour is because those were the units that were given to us in the first place. So that takes care of the magnitude. Next thing for us to take care of is going to be the direction. Now with that in mind, we are going to borrow something from polar coordinates, and it is that the tangent of theta is equal to y over x. Or in this case, that means that the tangent of theta is going to be the vertical component. Vertical component was 550 minus 30 square roots of 2 over the horizontal component, which was negative 30 square roots of 2. If I apply an arctangent to this, I will get an answer for theta. And it's going to be wrong, and I'm going to explain why in just a moment. When plugging this into the calculator, please be sure that your entire numerator and entire denominator are both inside an additional set of parentheses. So overall there should be a total of 3 sets of parentheses. So we'll begin by asking for an arctangent. It'll automatically generate the outer set of parentheses. The numerator gets its own set of parentheses. Close those off. The denominator gets its own set of parentheses. Oops. Square root's 2. And then we'll close those sets of parentheses. Now, before I ask the calculator for the answer, I'm going to verify that my calculator is in degree mode since I switch back and forth a lot. And now, I'll ask the calculator for our answer. This answer is incredibly wrong. Negative 85.222 degrees, we'll call that. Now, putting that in the context of the picture that we had up here just a moment ago, negative 85 degrees, if we were to draw in a horizontal and a vertical, negative 85 degrees is this direction. We want the exact opposite direction. And the way that we can get the exact opposite direction is by adding 180 degrees to it. So we'll point out that the actual direction is going to be negative 85.222 degrees. We'll add 180 degrees to that. So adding 180 degrees to our answer gives us that it's approximately 94.778 degrees. Now, the actual interpretation of that, 90 degrees, is due north. This is slightly west of due north. So I would refer to this as a bearing of 4.778 degrees west of true north. Now there is a shorthand for this, which is to say that we're starting north and then going 4.778 degrees west of that. This is a notation that you'll frequently see in our textbook. I will let you know that this is one way to do this problem. There is technically another way to do this problem. I'd like to show you that other way, just in case you prefer it. I'm going to head back to this piece of paper for just a moment, and I'd like to point out that the vector p and the vector w and the vector p plus w, if we take away their directions, then what you have here is technically a triangle. Now, when you're dealing with a triangle, we typically call those sides A, B, and C. Across from A will be alpha, across from B will be beta, and across from C will be gamma. We know 3 of these pieces of information, and that's enough to solve the rest of the triangle. In fact, I'm going to copy down my final answer right now. A, B, C, alpha, beta, gamma. In the context of the problem, here are things that we know. A represents the vertical side. That was the plane traveling true north. That side was 550. B was the wind vector. That side was 60 miles per hour. And technically, that means that gamma would be the angle between the reverse path of the plane and the reverse path of the wind, or I guess the path of the wind. Well, this direction was south, and this direction was southwest. I realize I'm casting a shadow on that now. This direction was southwest, and this direction is south. So gamma is the angle between south and southwest. We know that to be 45 degrees. This is an example of a side angle side triangle. I would like to find side C and angle beta. Side C represents the length of the sum of the plane and wind vectors, and beta is referring to the bearing. So let's go ahead and do that. Do I know exactly 2 angles? No. Do I have a corresponding angle side pair? No. That means I'm going to use the law of cosines. And because I already know an angle, I can use that to solve for the third side. So c squared is equal to a squared plus b squared minus 2ab cosine gamma. I'm going to plug in all the things that I know. So alpha is 550 squared, beta is 60 squared, minus 2 times 550 times 60 times the cosine of 45 degrees. That means that c is going to be the square root of all of this. That seems like the kind of thing that I want to just plug directly into the calculator without even messing with it. So with that in mind, when we did this the other way, I think we got something like 509. Let me see if I can find that. Oh my gosh, so many papers for one freaking problem. Yeah, here we go. When we did it the other way, we wound up with a magnitude of 509.34 miles per hour. Let's see what we get this. Oh, yeah, it's right there on the calculator as well. All right, well, that lesson learned. Plus 60 squared minus 2 times 550 times 60 times the cosine of 45 degrees. Fingers crossed, this should match what we got up here. What do you know? It does, exactly. 509.34. Well, let's hold on to a couple more places since we're about to use it anyway. That's miles per hour. Next, I'm interested in solving for beta. Now to solve for beta, I'm going to be using the law of sines. And I feel comfortable about that because I am not finding the largest angle of the triangle. I'm actually finding the smallest angle of the triangle. I know this because B is the smallest side. So sine of beta over B is going to be equal to the sine of gamma over C, meaning that beta is going to be equal to B times the sine of gamma divided by side C. Excuse me, sine of beta is equal to that. Beta will be equal to the arc sine of all of that. B is 60. Sine of gamma would be the sine of 45 degrees. And this denominator is that number that we just found. And if we did this right, the bearing that we got the other way was, what was it, 4.778 degrees? Well, let's see if we get 4.778 degrees by doing all of this. So extra parentheses for the whole numerator and extra parentheses for the whole denominator. I don't think we need it for the whole denominator, but I'd rather be safe than sorry. If this is 4.778 degrees, then we win. We win. Wow, this would make for a great, great test problem.